And today I would like to talk about examples of how to apply the equations which we discussed yesterday. Considering physics, we introduced concept of velocity, and we introduced concept of acceleration. These two quantities allow to predict us something, because really we introduce quantities so that we can predict what will happen. We want to know future, really. Science allows us to predict what will happen. If we construct something, for example, we want to make sure that it is going to stand. If we travel somewhere, we know that we want to figure out when are we going to get there, and therefore when to start a journey. And it could be a journey from here to Columbia or from here to Venus. Doesn't matter. Velocity is a quantity which actually allows us to predict when are we going to be where. Acceleration is a quantity, but we will learn pretty soon that from the configuration of the universe, when we see where what is, we can predict how that object will accelerate through Newton's second law. And from the acceleration we can calculate velocity, and from velocity where we are going to be. But these are the subjects which we are going to discuss in the future. For today, we know it just one way. So if we know where object is when, from that we can find out velocity, for which at this point we don't know what is it for. We can also find out acceleration, and also we don't see a purpose of that quantity at this moment. Both will be clear in pretty soon. We can actually continue with those derivatives further. So, for example, there is in automotive industry there is a quantity which refers to derivative of acceleration. People calculate the derivative of acceleration. You could have heard about it from TV. If you were interested in the science program, so it will be either on PBS channel or Learning channel or Science channel. Do you know? Have you? From the common knowledge, do you recall that quantity? Yes.
Is it torque?
No. Jerk. There is a physical quantity which is called a jerk, and actually, if I come and do something like this to JT, have you heard about word that to jerk something? Yeah, I jerked him. Yes.
I don't know if he's already said it. Did we say it's a change in acceleration?
Correct. Well, it's not a change acceleration. This is derivative of acceleration. It's more than that. It's exactly the relationship between jerk and acceleration is exactly like between acceleration and velocity. We have to calculate derivative of acceleration in order to get jerk. So it is rate of change in acceleration. In other words, change in acceleration divided by change in time. Or more precisely, infinitesimal change in acceleration divided by infinitesimal change in time, following Leibniz definition of derivative. Now, why automotive industry was interested in that? Well, because it is a theory that, a hypothesis that in an accident, how we are injured does not really depend on how our body is accelerated. If our acceleration changes slowly, we are able to adjust our body and to the condition of high acceleration. However, if that acceleration changes fast, very likely we will hurt our neck. All right. So how about if we start, if we now think about describing motions and trying to find out velocity and acceleration in this motion. Why don't we start with a very simple motion like this one, up to that point. So what was happening, you could see that position was changing proportionally to time. It was changing at a kind of constant rate. So position was a function of time. And now how about if you write down that function, this function of time? Well, car had one position at any instant. However, if we think about a vector which we assign to that position, we can do it in a lot of ways. And then if we assign a vector, an arrow which identifies position, in many ways we can assign arrays of scalar components, or the scalar components. So when you have this kind of a problem, be smart. Do it in such a way that the equations are not too complicated. All right, so how about if we start with assigning an arrow? Where would you choose the reference point to assign an arrow indicating position of that car? Well, in principle, actually, you can put it at the tip of your nose, which will be good, actually. And, well, so there will be an arrow. If I did that, it will be an arrow from the tip of my nose. And let's say that, I suggested actually that as long as we, because right now I want you to think about objects as particles, so it is supposed to be a point, and I suggested that if you do it as a point, you should choose a point which is referred as the center of mass. At that point, you can imagine that it is something like a geometrical, that it is somewhere near the object, and its geometrical center. Although you can, for example, choose this light over here as that point as well, because when that car moves, most of points constitute, or particles constituting this object, move at the same rate. Wheels only do it differently, because in the wheels some of the points move up, some of the points move down. There are points which don't move at all, and there are points which move twice as fast as that car. So for a moment, think about this one. All right, so so I could indeed think about an arrow from my nose to that red point over there. Is it the simplest one? Can you find a simpler one? Let's do it that way. Yeah, that one is smarter. So how about if I choose that point as the reference? So at this instant, position would be 0, correct? And as car moves further and further, we will have a horizontal arrow to the right. That one is much easier than an arrow like that. Although for calculation, both would be good. All right. So, what kind of a car is that? So it means that we choose somewhere a point, this is already moving. An arrow like that represents now position at when I released it, this point was here. All right, so this arrow represents, this is the position vector. And actually now we can imagine, these arrows are really good to imagine the problem. However, to perform calculations, I suggest that we do it on scalar components. So how about if we assign scalar components now to position and do it also smart? How many ways do you recall in how many ways we can assign scalar components? Infinite, right? Depending on this, because I picked this point as the origin now. Depending on this, how I choose the base vectors, vectors I, j, and k, or in other words, how I choose the reference frame, I can assign those numbers in many ways. Yeah, I can choose them like this, like this, like this, like this, like this. Suggests to me so that the calculations are simple. Tell me if it is easy or not. If I, let's say, do it that way. No, it's not easy. How about if I do it like this? Yes, right? If I choose I, j, and k that way, it will be easy, because if I do it that way, scalar components of the vector. So how about if I think about it? Yes, I will choose vector I in this direction. So this will be the direction of x-axis. Up will be y-axis, and z-axis toward us. Because indeed this was a smart choice, because I can quickly say where the particle is at an arbitrary instant. So scalar components at instant t, two of them we know immediately. We know what will be y and what will be z at any instant if we choose coordinate system in such a way that that selected point moves along x-axis. If point moves along x-axis, what are the x and y scalar components of its position? 0 all the time. Very good. So I have that y is 0 and z is 0. Now x component is proportional to time. So I can write it down as a certain number multiplied by time. I'll put that number over here. Just a random number from the alphabet. How about if I choose it V? I picked randomly letter V to represent a number. If we now think about, it would be good also to include the units. So, think about the units. So, position. In an SI system, components refer to position. So we use the same, and really it's kind of, if it is to the right, it refers to the distance from the origin. If it is to the left, it is opposite to the distance. So the unit of position is the same as unit of distance, which means that it has to be in meters. In SI unit, all scalar components are measured in meters. I could put meters over here. How about if I put meters? Now, we measure time in seconds, which means that this coefficient will have to have a unit of meters per second. Yeah. So if this unit has meters per second, this one is in second. If I multiply those two, I will get meters. How about if I put then meters? I will get rid. Let's leave these meters here. Now I put here V, meters per second, and T seconds. All right. Let's now find velocity of that object at an arbitrary instant. And Josh maybe can help me. Josh? Are you Josh? Because yesterday Josh was confused about derivatives. Do you know how to do it now?
Do I know how to do a derivative now?
Right. Well, I forgot actually I have not covered one slide yesterday. So so maybe let me make a digression. If we have a function which for which we know scalar components, so let's say that we have a certain function and scalar components of this function are functions of time. Then, when we calculate the derivative of this function with respect to time, by definition, it is limit as the argument, change in argument approaches 0 of the difference quotient. And in the difference quotient, I have to write down over here function at instant t plus delta t, function at t plus delta t, and z of t plus delta t minus the value of the function at instant t. Which means I have to calculate limit, and let's perform operation of addition, yes?
Would the delta t at the bottom be the total time?
No, this is just change in argument. Delta t in the denominator refers to change in the argument. Total time of what? Recall the definition of derivative. We said that when we calculate derivative at a particular instant, we see, at a certain value of the variable, we see what will happen with the next value of variable, by how much the function is going to change, and take the quotient. In other words, we construct the difference quotient. Change of the function divided over change in the argument, and it has nothing to do with the total. It's just change in the argument. And now for an arbitrary change, we will get certain value of the difference quotient. We have to continue it using various changes in argument and get them into a sequence such that the change in argument approaches 0. We will get a sequence of difference quotients, and to whatever that sequence of different quotients converges, to whatever value, that value is referred as the derivative. All right, so now let's perform the operation of this addition. I can combine it into one vector. So scalar components of this vector are going to be x of t plus delta t minus x of t, y of t plus delta t minus y of t. And for z, we will have z of t plus delta t minus z of t. And actually, I'll do something, one more thing. Since here I had to divide multiply this entire vector by number 1 over delta t. I can perform this operation because, on each component. So I have to multiply each component by this number, which means that I will have over here delta t. Over here I'm going to have delta t, and over here I'm going to have delta t. Now I will have to imagine what will happen. So for a single delta t, I will have difference quotient for x component, difference quotient for y component, and difference quotient for z component. Now I'll change delta t to a smaller one. I will have certain value here, certain value here, certain value there. I take delta t smaller. I will have certain value here, certain value here, and certain value here. So I will have a sequence of numbers for the first component. I will have sequence of numbers for the second component, and I will have sequence of numbers for the third component. And these sequences will be with delta t approaching 0, which means that really I will calculate, when I calculate that, I will have a sequence limit with delta t of x of t plus delta t minus x of t over delta t, limit for the second component and limit for the third component. Now, can I recognize what's that? It's limit of the difference quotient for the first component. Derivative. Derivative of what? Nope. It's not the derivative of position. Not the derivative of velocity. Talk to each other, it's derivative of what? Because we started with the derivative of position. Here we calculate derivative of position. Over here we got something else. Consult with each other what we got here. And it's not the derivative of position, it's not the derivative of velocity. It's not velocity either. Not acceleration, it's even worse. Consult. I mean, try to talk to each other rather than guess. Yet, talk to each other. What are we getting here? What is that? Of the x component of position. Correct. Here we have the derivative of the x component of position. Oh, right. So, here we will have one number which represents derivative of x component of position. I will write it down that way. What am I going to get here? Say it in English now. Derivative of the y component of position. And over here, derivative of the z component of position. All right. Now, right, I mean, provided that f was function, that the function represented position. That's fine. Now, x component, derivative of position. What derivative of position gives me? Correct. Which means that over here, that array represents what? Correct. This entire array represents velocity. And what is that? We don't call it velocity in the x component. I want you to use the same nomenclature as for every vector. If I have a vector A equal, so that scalar components are AX, AY, and AZ. AX is what? We don't say that it is A in X direction. We say that it is not magnitude, the x component of vector A. All right, so say it now for velocity. This is x component of velocity. Well, I will now summarize what I got over here. We were doing it for position, so function f represented position here. But in general, I can think about it that it's an arbitrary function, so x and y and z just don't represent components of position, but something else, certain quantity. When we have a vector-valued function of time, then when we calculate rate of change of this vector-valued function, we find out that scalar components of the derivative are equal to derivative of scalar components of this vector. I think that phrase was really confusing, so make sure that your neighbor understands it. Consult with your neighbor. What did I just say? Let me repeat it. Components of the derivative of a vector are equal to derivative of components of the original vector. I know, because right now I think that half of you just heard a sequence of English words. And it didn't matter if I said it in English or in Polish. Therefore, I want you now to consult with the neighbor. What am I saying? Let me repeat it again. Because I can repeat it as many times as I want. I can do it even standing on my hands if I could. Because it's obvious for me. However, for you it isn't. Derivative of a component of a vector Oh, now I'm confusing myself. How did I say? Oh, no, I said that. Now, when we calculate the derivative of a vector, we will get a vector whose components are equal to the derivative of the components of the original vector. This makes sense? Okay, no. And now let me show it to you. When I take derivative of a vector valued function, I will get a vector whose components are derivatives of components of the original vector. In other words, if I want to calculate derivative of this function, I will get a vector whose first component is derivative of the first component. Second component is derivative of the second component. Third component is derivative of the third component. Do you understand that? Make sure that your neighbor understands it. No, don't just ask, do you understand it? Ask the person to repeat my sentence. And actually, let's go even further. Well, we have already written a function for that card. Consult with your neighbor before I perform operation of differentiation. Let's find scalar components. Consult with your neighbor how to find scalar components of that velocity over there. Consult with each other now. Do you know? Do you know it? Now, who knows it? Do you know it? Do you have an idea what should we do in order to find out now velocity, which we recognize that it's a derivative of position? Do you know how to do it?
No.
Who knows it?
Take a derivative of ET, derivative of 0, derivative.
Correct. We have to take derivative of the three functions which we have in the position vector. Here, x component is a linear function of time. Y component is a constant function of time, and z component is a constant function of time. So when I calculate derivative of position, I have to take the first component is going to be derivative of x component of position. Derivative of the second component is going to be, second component is going to be derivative of second component of position, and third component of velocity is going to be derivative of the third component of position. All right. Now, if you look at the appendix at the derivatives, what kind of functions do we have here? Here we have a certain constant multiplied by a function. If you take a look at the in the appendix, there is a formula which says how to calculate the derivative of a power function. It says that if you want to calculate the derivative of function x to the n, then it is going to be n times x to n minus 1. Now, actually, probably, and now I realize that it would be nice if I included one more formula, which actually results from the product rule. Let's say that I want now to, that I have a function that it's a certain constant multiplied by x to the n, and I want now to find out the derivative of this function. Actually, how about more general? Let's use product rule to find the derivative of a function which has a constant multiplied by a function. So, according to product rule, I have to calculate first derivative of I'm not going to derive it now. I just want you to recognize that if we multiply a certain function by a number, then derivative is equal to that number multiplied by the derivative of the function. We can pull out constant in front of the function. All right, this is what we have here. We have a certain constant multiplied by a linear function. So if I think now that x, if I substitute t for x over there, n would be, what would be n in our function? Just 1, correct. So there's like calculating d over dt of t to the power of 1. Well, according to this formula, I will have that this is 1 times t to the power of 1 minus 1, 0, which means that it is going to be 1. All right, which means that if I calculate this component, I will have v, which is a constant corresponding to a over here, times constant value 1. So it will be just v. Let's now calculate derivative of 0. I can imagine that 0, that I have that this value is 0. Yes, so derivative of 0 is going to be 0. And derivative of the second 0 is going to be also 0. Now when we calculate derivative, now that numerator over here is in meters, this is in seconds. So the units are meters per second. We got an expression that velocity of this cart is going, that constant which we had over here, times 0 times 0. How velocity changes in time according to this formula here? Is that velocity, the value of velocity, well, what happens as time passes by? The velocity is the same, correct. That value is this function is a constant function of time. And because of that, the motion which we just observed is called a motion with constant velocity. Sounds simple, but I think you will forget it by tomorrow. So why don't you say, what type of motion did we discuss a moment ago? Motion with constant velocity, correct. Well, let me ask you something then. Let's find out acceleration in that motion. Why don't we find out how that object accelerates? What do I have to do? I have to calculate the derivative of velocity. All right. Well, I can think that this function is v times 1. I can take v in front as a constant and calculate the derivative of 1 using this expression. What value for n should I take so that x to n is 1? 0, correct. X to 0 is 1. So now when we calculate derivative of 1, it is like calculating derivative of x to 0. If I calculate x to 0, what am I going to get on the right-hand side? I will get that 0 over here, x to negative 1. How much is that? 0, correct. So the derivative of 1 is going to be 0. I will have number v multiplied by 0, so the derivative, so it means that this derivative is 0. So x component is 0. Whenever we have a constant function, derivative of a constant is 0. Remember that, it's useful. Derivative of a constant is 0. How about derivative of 0? Also 0. 0 is also a constant. And 0. What would be the units? Newtons per second square, because it would be, this one is dvx over dt. dvx was measured in meters per second. dvx is change in x component of velocity. Say it to your neighbor. What is dvx? Right. If we divide it by time, we will get meters per second square. And in a motion with constant velocity, acceleration is always 0. How about jerk? I don't believe it. Convince me. Can you convince me that jerk in this motion is going to be 0 vector as well? Because there is no change in acceleration, so when we do something, we'll get vector 0, 0, 0. What is that something? Derive how? We will derive jerk. How? By doing what operation? Finding derivative of derivative of acceleration. Correct. Good. I think that I won't go to the next motion now. I'll do it tomorrow. However, before you go, tell your neighbor how to find the derivative of a vector. Right? So can somebody, all right, what you were supposed to say to your neighbor, that the components of the derivative of a vector, correct? Component of the derivative of a vector equals to derivative of the component of that vector. Good. Thank you very much. So this will be all for today. See you tomorrow.